Bismillahirrahmanirrahim. My name is Waqas Ahmed Khan, and I am working as lecturer in Department of Chemical Engineering. Today, our topic is combustion analysis, which is very important in many industrial operations. What is combustion? I will briefly explain, and then we will go for some calculations of combustion. Initially, combustion is a fast chemical reaction between some fuel and some oxidizing agent. And that oxidizing agent is most probably air. And we will calculate that air. So the calculation of air is very important in combustion analysis. Now, now, combustion has many applications. Like combustion reaction is used in power plant for generation of electricity, in boilers for steam production, industrial furnaces, petrol engines, diesel engines, gas turbines, and different domestic cooking and heating sources. So understanding combustion is very important. Now, before going to the topic, uh, I would explain that what are the essential ingredients for to complete a combustion reaction. One is that combustible component. It can be either solid fuel, it can be in liquid fuel or gaseous fuel, and the other one is that incombustible, that oxidizing agent, which is also important. And somehow we need some source to ignite to start that combustion reaction. So here in this specific lecture, we will conclude that how we get to know that what is the percentage of that oxidizing agent, specifically that air, is needed for some specific composition of combustible component. So most of the fossil fuels that are combustible, that consist of combustible component and non-combustible component. So we have uh, two types of components in all the fuels. One is known as combustible components, and the other one is known as incombustible components. The combustible components are readily in the form of solid fuels, liquid fuels, or gaseous fuel. In solid fuels, the components are carbon, sulfur, and hydrogen. Similarly, in liquid fuels and in gaseous fuel. And the non-combustible part is nitrogen, oxygen, ash, and moisture content. So these are the non-combustible part of combustion. Now, let us move forward. Now, look at these reactions. These are most probably the reactions which occur during a combustion. Supposingly, we have carbon and it goes on react with oxygen to form carbon dioxide. When this oxygen supply is limited, then we have incomplete combustion. And if furtherly we give the complete oxygen supply to this carbon monoxide, then it goes to form carbon dioxide. So usually we all that fuels are combustible, and we have same oxidizing agent, which is oxygen, and that is most probably coming from the air. So we have dry air contains 21% of oxygen and 79% of nitrogen by volume. So 1 mole of oxygen carries 3.676 moles of nitrogen. So based on this proportion, we will go on some combustion analysis and reaction combustion reaction, and then further we will complete the calculation of combustion. Now let us start the things. How can we solve some combustion problem? These are the 7 steps which are used, which are journal step, and if you follow these steps you can solve any type of numerical or problem regarding combustion. And you need some theoretical air requirement, so you can find theoretical air requirement of any type of fractions if of fuel. Initially, what you do, you just write a combustion reaction, and all the combustible or non-combustible, most probably combustible elements which are present in your fuel. So you have to write these combustion reactions, and then you have to calculate the weight of oxygen required for that complete combustion. Then you have to subtract the oxygen already present in the fuel, and then you have to calculate the weight and volume of air. At last, you will convert that weight of air by multiplying 100. As we know, by weight it is 23% of oxygen in air, and by volume it's 21% of oxygen in air. So we have to multiply by this factor to get the total amount of air. So let us do some practical performance or numerical to find that actual amount of oxygen in our in any kind of combustion problem. This is a lab analysis of some this is an analysis of a fuel in some lab. 85% content is carbon and rest is hydrogen. 12% oxygen already present, 0.7. We have to, at the end we have to subtract this already present oxygen, then nitrogen, sulfur, water and ash content. Supposingly we have to select some bases, so we select 100 kilogram of our furnace oil, and the molecular weight of all the ingredient present in that fuel oil is written here. It's 12 for carbon, 32 for oxygen, hydrogen 2, sulfur 32, and rest is 28, 44, 64, and 18. The first step which we have to do is to write the balanced chemical equation for all the combustible parts. The combustible parts in these ingredients are carbon, hydrogen, and sulfur. So carbon goes to react with oxygen and goes to form carbon dioxide. If it's complete combustion, then we have hydrogen, and we have sulfur to form sulfur dioxide. These are the chemical reaction. Now let us consider the first reaction, and we have to follow some basic rules. This is one molecule of carbon goes to react with oxygen to form carbon dioxide. So in simple words, if I want to explain this, that the molecular weight of carbon is 12, the molecular weight of oxygen is 32, and the molecular weight of carbon dioxide is 44. So in very simple words, 12 kilogram of carbon requires 32 kg of oxygen if it's want to react for complete combustion to form 44 kilogram of carbon dioxide. Now, in our case, the carbon is not 12 kilogram. It's 85.9 kilogram as the laboratory fractions tells us. So we have to apply unity method to find that what is the oxygen requirement for our case. So we just divide the whole terms by 12 to get their one, the unity method, and 1 kilogram of carbon requires 32 divided by 12 kilogram, that is 2.6 kilogram of oxygen. Now this is for 1 kilogram, and we have, as we know, that we have 85% here, 85.9% of carbon. So just multiply 85.9%, which will tell us the required amount of oxygen. Similarly, consider the second reaction. Same is done with the second reaction. 4 kilogram of hydrogen required 32 kilogram of oxygen to form 36 kilogram of water. Again, we apply unity method. Here we divide the whole equation numbers with 4. We will get 1 kilogram of hydrogen required 32 by 4 kg, that is 8 kilogram of oxygen. And in simple words, as we have 12 kilogram of hydrogen already in our laboratory analysis, so we get that the oxygen required is 12 multiplied by 8. Similarly, in sulfur case, the balanced chemical equation is sulfur plus oxygen goes to form sulfur dioxide. So simply here we again 32 kg sulfur requires 32 kg of oxygen to form 64 kilogram of sulfur dioxide. So for 1 kg we have to divide the whole numbers with 32, and we find that 1 kg of sulfur requires 1 kg of oxygen. So we have already zero point 0.5 kg of sulfur in the laboratory analysis. So at the end, we got the three numbers of oxygen. The first number comes from the first reaction, the second number comes from the second reaction, and the third number comes from the third reaction. Then we add up these three numbers. 229 comes from the first reaction, 96 comes from the second reaction, and zero point 0.5 come from the third reaction. This is the total oxygen required to carry on all these three reactions. But wait a minute, we have some oxygen present in our laboratory analysis, that is zero point 0.7. Initially, I told you that this zero point 0.7 should be subtracted at the in the last, and we have to subtract this. So we subtracted this additional oxygen required. So the net oxygen required is 324.87 kg. Now, this is the amount of oxygen, but we don't have oxygen, we have dry air, so which contains about 23% of oxygen by mass. So we have to calculate the amount of air, not the oxygen. Oxygen is 324. If you have a clean oxygen present and you want to use for this for combustion, then you can take 324 gram. For this fraction that is comes for these figures which comes from the lab analysis. But if you want to use air instead of oxygen, then you have to divide this factor 0.23 or multiply 100 by 23 to find the weight of the air required. Now, the weight of air required is 1412.45 kilogram of air that is required. Initially, we take the basis of 100 kg, but here we have to find for 1 kg. So for 1 kg, you have to divide that 100 kg, and you can get 14.12 kg of air required for 1 kg of fuel that is analyzed in the lab, and which fraction should be this. So this, if you use this fraction, it will completely burn, this fuel will completely burn and give you the maximum output of the maximum calorific value. If you use air below this value, you will get some you will get some lean solution, and if you will use this more than this, then you will get a rich solution. So you have this is the best stoichiometric ratio which can be used for this fuel which is analyzed in the laboratory. Similarly, you can do the same calculation on the coal, and you can find that the theoretical air required for your required quantity of fuel to burn. So this was a simple explanation for the combustion analysis. Thank you very much.